Good morning. In this talk, I'm going to discuss the paper Macroscopic Superpositions in Isolated Systems, written with Roman Buniy. And this paper appeared on the arXiv in, I think, late 2020 and will appear in the journal Foundations of Physics. The outline of the talk is given here. I'll start with a kind of informal setup and description of the result that we prove. Informally stated here, it's a theorem to the effect that a complex quantum system, so a system with many interacting degrees of freedom, which is evolving according to the Schrödinger equation, will spend almost all its time in a macroscopic superposition state. And I'll define more carefully or more explicitly what is meant by a macroscopic superposition state. But the observation is very general. So it's an isolated system, a bunch of atoms in a box interacting with the ball. So that's the Brownian motion setup, which we use as an example in the paper. And if you let that just evolve by itself according to the Schrödinger equation, if you wait long enough, the system will evolve into a macroscopic superposition state, and it will spend almost all of its time as t goes to infinity in that kind of state. So to prove this result, we use two different kinds of machinery. First, I'll talk about something called concentration of measure in high dimensions. And this is really a statement about the geometry of spheres in a high number of dimensions, which then can be applied to quantum mechanics. And this particular machinery makes it very plausible that the result is true. It shows that if you randomly sample a point from the Hilbert space describing this complex system, it will have the desired properties. However, it's not a dynamical statement. It's not a statement about how time evolution under the Schrödinger equation causes motion on this high-dimensional sphere. And to obtain that result, we use something called von Neumann's quantum ergodic theorem. This theorem has a very curious history. The theorem was proved by von Neumann in 1929, and this was in a very early stage of the development of quantum mechanics. And of course, both von Neumann and others like Einstein and Pauli and Schrödinger were all also very familiar, obviously, with statistical mechanics. And so the important problem of connecting the new quantum formalism with what was known already in classical statistical mechanics or quasi-classical statistical mechanics was quite an important problem. And von Neumann proved this theorem in a very long paper. It's, I don't know, depending on the way you print it out, it could be 50 or 100 pages long. And the results are proved in great detail, and they were well appreciated by people like Pauli and others, Schrödinger, who read it and corresponded with von Neumann. But the paper was written in German and was only translated to English just in the last 10 years, in the 2010s. And interestingly, the main results of the theorem were forgotten, were really largely misunderstood. In fact, there are only a couple references to the paper in textbooks on quantum statistical mechanics that appeared, say, I believe in the 50s. And those books actually misunderstood what von Neumann had proved. And so it's only in recent years, actually, that people have really returned to this theorem and understood it better. And we make use of it here. In the final section of the talk, I will discuss how these results can be reconciled with the common intuition that physicists have that macroscopic superpositions are fragile. In other words, if you try to set up some really complicated superposition state, for example, in a big quantum computer, that configuration is very fragile, and allowing it, for example, to interact with the environment or some other degrees of freedom quickly destroys the macroscopic superposition state. And I'll explain how that intuition is nevertheless consistent with the results that we prove. In order to do that, I have to make a slight detour into quantum measurement, decoherence, and the discussion will also touch on something called many worlds quantum mechanics. So let me begin with section 1 of the talk. Let's consider as a very explicit setup, a very explicit system to concretize all the ideas, the familiar example of Brownian motion. So imagine we have a box, and in the box is a solid ball. I emphasize it's solid because the gas molecules that are also in the box are not allowed to occupy the same space as the ball. And other than the ball and the gas molecules, we just have an isolated box. So there are no interactions with any outside world outside the box. But there are interactions, of course, between the atoms and each other, the atoms and the ball, and one can even include, for example, the Hamiltonian of the individual molecules inside the ball. And so the Hamiltonian might be written a Hamiltonian for the ball, Hamiltonian describing the atoms, and a Hamiltonian describing the interaction between, say, the ball and the atoms. Now, it's already familiar from Brownian motion that there is a non-zero quantum amplitude for the ball starting, say, at position X to random walk to some other location Y, and that location Y could be macroscopically different. So imagine that the box is a meter cubed. There is a non-zero quantum amplitude given enough time for the ball to start at position X and random walk to position Y, which is, say, 10 centimeters away. And obviously that's a macroscopically different configuration of the system. So I think that part is not surprising. What is interesting is the dynamical result, that if I let the system evolve, and formally in the result of the theorem, you're letting the system evolve for an infinite amount of time, but it turns out that's not really necessary to get where you need to go, and I'll explain that in more detail later. But if you let the system evolve long enough, it actually will evolve into a macroscopic superposition where psi, lowercase psi sub nu, describes different positions and momenta of the ball, and phi sub nu describe the configuration of the atoms. And the system will evolve into a state like the one written here, which is a superposition of ball in different places and the corresponding, quote, environmental state of the gas molecules. And here, the notation that we'll adopt for the rest of the talk is that the symbol nu labels distinct macroscopic states of the system. So again, familiar system, Brownian motion, familiar that the ball has quantum amplitudes to walk or random walk around the box. Perhaps not so familiar that if we wait long enough, the state of the system will assume a kind of very characteristic form, and that characteristic form will involve macroscopic superpositions. Okay, so we can write out the ball Hamiltonian quite explicitly. Let P and Q be center of mass, momentum, and position, respectively. There can be a potential, which is a function of the center of mass position of the ball. So, for example, the floor of the base of the box might be slightly curved or something so that V of Q is non-zero. But we'll just assume in discussion here that it's fairly weak and it doesn't have a strong impact on the dynamics. And one could even write out terms P sub I squared and Q sub I, which describe the internal degrees of freedom, the individual, say, molecules which make up the ball. And there can be interactions among those molecules that bind them into the ball. And importantly, a result from elementary quantum mechanics is that you can write out this Hamiltonian in such a way that capital P and capital Q commute with the individual molecule, or so-called relative degrees of freedom, describing the internal state of the ball. We're going to focus on capital P and capital Q. Now, at the beginning, capital P and capital Q are full-blown microscopic quantum operators, but it's going to be useful to define macroscopic versions of the operators P and Q and the corresponding eigenstates. So what do we mean by a macroscopic version of an originally fully quantum microscopic operator? Let's start by talking about the macroscopic energy of the box, the total energy of the box. Now, obviously, it's beyond our capability to measure the exact microscopic energy of all the degrees of freedom together in the box, which would be given by the sum of H ball, H atom, and H interaction. The level spacing between those energy eigenstates could be exponentially small, and our current technology doesn't allow us to measure it. So for practical reasons, or to make contact with actual experiments, we usually think in terms of a macroscopic version of the total energy or of the Hamiltonian. And that is a coarse-grained version, where we say, well, we measured the total energy in the box, it's roughly 62 ergs, and but there's some residual tiny uncertainty to the energy. And so in order to define a macroscopic version of the Hamiltonian, typically what we do is we coarse grain by grouping together energy eigenstates or energy eigenvalues that are close together, that are in bands. And so we end up talking about energy shells rather than specific energy eigenstates. The characteristic properties of these bands are that there should be many eigenvalues in each band, and the energy difference between bands should be large enough that potentially they're experimentally accessible. So you could tell the difference between a box that's in band 1 and a box that's in band 2. However, you aren't necessarily able to tell the difference between energy eigenstates which are within a particular band. So to define this new operator, we would then assign all the eigenstates in a particular band a particular coarse-grained eigenvalue, which might be the average of the specific eigenvalues for all the states in the band. And this, of course, means that the macroscopic energy operator has very large degeneracies, which just means that because we can't tell the difference between specific energy eigenstates of the box, we lump together a bunch of them and we assign a particular macroscopic eigenstate to that band of microscopic states. This procedure can be generalized. So imagine that I give you a microscopic operator A. It might be the capital P that describes the momentum of the ball. It might be the capital Q, which describes the center of mass coordinate of the ball. And in general, that operator will have some eigenstate expansion in terms of basis states little a. And we can obtain, in a similar way that we just did with the energy, we can obtain a coarse-grained or macroscopic version of the original microscopic operator. And this is again done by dividing the sum into bands of nearby eigenvalues and replacing the coefficients A in the eigenvalue expansion with the average within the band. So in the bottom of the slide, I have an example. Now, of course, I don't have enough space to write out the huge kind of matrix that I would need to describe one of these operators, A, capital A. This is just done in terms of 4 basis states. Initially, you have capital A eigenstates 1, 2, 3, 4 with eigenvalues little a1, little a2, little a3, little a4. And it might be that A1 and A2 are kind of close together, so we decide to group them together, and A3 and A4 are close together, so we decide to group them together. And we define a new operator in which the eigenvalues are given by little a, which is perhaps the average between A1 and A2, and A prime, which is the average between A3 and A4. And you can see in this manner I can define, actually it's not a unique definition, but there are many different families of macroscopic versions of the original microscopic operator. But once I'm specific and I define the macroscopic operator that I choose to work with, at that point, that operator itself has a well-defined Hilbert space, a well-defined set of eigenvalues, etc., and I can use that for further analysis of the system. And this approach was actually laid out very clearly in von Neumann's paper. And just as a matter of historical interest, this is a kind of thing which, when I teach quantum mechanics to students, they're often interested in how do you connect these microscopic operators involving, say, single electron states to some more macroscopic measurable property of a system. And the explanation of all of this is very clear in von Neumann, but in general, it's not to be found in most textbooks on quantum mechanics. So I think it's useful for anyone who's a professor and teaches that kind of class. It's useful to think about this, and it makes it a little bit easier to explain to students when they first encounter quantum mechanics what is the connection between the microscopic and macroscopic world. Okay, so an important property of macroscopic observables is we expect them to be measurable simultaneously. So in other words, the corresponding macroscopic versions of, for example, capital P momentum of ball and position Q of ball, they should be constructed in such a way that they actually commute, so that I can diagonalize P and Q simultaneously. And again, the analysis for this is done in some detail by von Neumann. It basically involves constructing wave packet states which have a well-defined central value of P and Q and a spread which is small relative, say, to, or of order, typically the band size. And of course, then it doesn't violate the uncertainty principle, but it is much more convenient to work with these orthogonalized, simultaneously diagonalized P and Q in the further analysis. Now, once you've defined these simultaneously diagonalizable macroscopic operators, then you can define what in sort of classical statistical mechanics you would call phase space cells. So you can define little cells in the microscopic state space in which the system, or the ball in this case, has a macroscopic value of momentum P and a macroscopic position Q. And we will use the symbol nu to label individual phase space cells. And this notation is originally due to von Neumann. Okay, so the first piece of machinery that we're going to introduce is called concentration of measure. And this is really an observation concerning, as I mentioned earlier, geometry of high-dimensional objects, in this case spheres. And using these results, we can prove the following. For any subspace of a large system, and in particular the subspace of interest could be the subspace defined by the set of macroscopic observables that we just defined, the density operator rho 1, where 1 labels the subspace of interest, so in this case subspace of macroscopic observables, the density operator rho 1, which is induced by tracing over the other degrees of freedom, so that would be, in this case, in Hilbert space 2, would be all the gas, atoms, any other degrees of freedom that we're not focused on. When we trace over all of those other degrees of freedom, a random pure state describing the whole system after taking that trace, is overwhelmingly likely to be close to have density matrix rho 1 close to the identity in the subspace 1 with the normalization factor 1 over the dimensionality of subspace 1. And actually, if you're very familiar with density matrices and this kind of formalism, you might immediately notice that this kind of proves the result that we want. But I won't expect the audience to actually follow that, and I'll go into that in more detail later. But this is almost the result that we want to prove. Now, based on the dominance of the measure, okay, so given that a random pure state is overwhelmingly likely to have this property once we trace over the subspace 2 degrees of freedom, that almost proves the theorem, because if the space of the state space or the Hilbert space is completely dominated by configurations that have the desired property, then any dynamical evolution is likely to spend most of its time in that dominant submeasure of the space. And so even if I start with a configuration like ball is strongly localized at X, and this in that initial state, trace over subspace 2 leads to a row 1, which deviates strongly from the one that's written here on the slide. Even if that's true, you would expect that any reasonable kind of dynamical evolution would cause the system to move around in the space and eventually spend most of its time in the much larger part of the geometry. So the concentration measure result almost proves the result, but we need further dynamical information or dynamical analysis, which is provided by von Neumann to fully prove the theorem. So let me go through some of the calculations involved here. So we do this very explicitly in the paper. And I guess to really follow the details here, since they're quite a welter of indices here, I suggest you actually look at the paper because it also has an appendix in which some intermediary results are given, which are not presented in these slides. But what I'll do is just kind of sketch out the calculation. I don't expect people to really be able to follow it on the slides in real time. So imagine now we have two complete sets of orthonormal eigenstates for two Hilbert spaces, 1 and 2. 1 could describe, for example, the macro observables that we're interested in. 2 would be everything else. We define a pure state in terms of these coefficients C sub J1, J2 in this Hilbert space. And then we can define a density matrix rho, which describes the original state psi. And then we can describe a restricted density operator rho 1, which we obtain by tracing over the 2 degrees of freedom. So we take rho and then we trace over the 2 degrees of freedom to get rho 1. So these are just standard expressions, but we've chosen a notation here that makes the calculations, I think, very concrete. Now, the Hilbert space of a normalized quantum state has the geometry of a high-dimensional sphere because you have a constraint on the sum of the squares of these coefficients, C, J1, J2. And it's the same condition that guarantees that trace of rho and trace 1 of rho 1 is equal to 1, which is the standard condition on a density matrix. Now, what's interesting then is any property of this state or these density matrices can be translated into a geometrical statement about the properties of points distributed on a sphere in a high number of dimensions. And so, for example, it's straightforward to calculate the expectation of CC star, which is necessary to compute rho. And then furthermore, to take the trace of that resulting tensor with respect to the subspace 2. And so you can also very quickly calculate the expectation of the density matrix rho 1. And it has the form that I gave on the earlier slide, that it's proportional to the identity matrix with the required normalization factor n1 inverse. Now, those are just the expectation values. So in just a few steps, you can show that the expectation value of rho 1 is exactly what you want. However, you can make much stronger statements. So you can show that for states that are uniformly distributed in the Hilbert space, or equivalently points that are uniformly distributed on the high-dimensional sphere, that the values of rho 1 are strongly concentrated near the expectation value. And for this, we use a very famous lemma from probability theory, or you could call it either probability or high-dimensional geometry. Levy's lemma implies that for any function from the sphere to the real numbers, assuming that f is relatively smooth, not too unsmooth, a uniformly distributed random variable c on the sphere will satisfy a concentration bound, which says that the probability of finding a c such that the function f of c differs from its expectation by more than epsilon goes to 0 very fast as epsilon gets large, goes to 0 exponentially rapidly with the dimensionality in which we're working. And the only thing that weakens the bound is this Lipschitz bound or Lipschitz norm on the gradient of f with respect to c. So in other words, the more jagged the function, or the more rapidly varying the function f, then the weaker the bound gets. But if you can put some upper bound on the rate at which f varies as you move on the sphere, then you get a concrete probability bound on the deviation of any function of coordinates on this hypersphere from its expectation. And so this is a very famous lemma. It's used to prove all kinds of results in probability, relating probability to high-dimensional geometry, and has recently been used in statistical physics. So now in our case, we have a very explicit form for the density matrix rho 1 that we're interested in. It's quadratic in these variables c. And so it is itself bounded in norm, the gradient is bounded, and so we can explicitly calculate probability bounds on deviations of the diagonal terms in the density matrix from 1 over n1, and also deviations of the off-diagonal terms from 0. And these results are given here in equations 8 through 10. In particular, as n1 times n2 becomes large, we get very strong concentration, which is the desired result. Note that the only thing that's required to be large to obtain the result is n1 times n2. So the subspace 1 that we're interested in could be quite small, could just perhaps have just a few degrees of freedom. But as long as n2, or the product n1, n2, is large, then you get the concentration result. So in particular, you might be looking at a relatively small macroscopic or coarse-grained set of degrees of freedom, but if there are lots of other degrees of freedom that you're tracing over, you still get this enormous concentration. Now, in fact, in detail, these bounds that we derive in the paper are new in the literature, and they're quite a bit stronger than other bounds that have been derived using Levy's lemma in the physics literature, or actually in the math literature as well. And you can see actually from the form of this that concentration starts to hold as long as n1, n2 is somewhat large, say, compared to, say, numbers of order 1. So say large compared to 4, for example, if you look at equation 8. And so if you have even just a half dozen qubits, imagine you have a quantum system which is half dozen qubits or 10 qubits, and you want to ask some questions about how the measure is distributed or how some average quantities behave, etc. You can actually use these bounds already, even with, say, a half dozen qubits. That Hilbert space is large enough already for these concentration effects to start to manifest. Now, again, the goal here was to prove that rho 1 is highly likely, in terms of most of the measure that the system can explore in its dynamical evolution. Rho 1 is highly likely to be proportional to I1, the identity on subspace 1. And what that means physically is that you have a superposition state because you have support for different, in the case of Brownian motion, different macroscopic positions of the ball. I'll come back to that and try to clarify that in a bit. Okay. Now, as I mentioned, the concentration results don't give you the full result that you want, because the concentration results just talk about the measure on the sphere or the measure in the Hilbert space. And to get the final result, you want to say something about how the system evolves. So given, say, a state which deviates, which is in a subset of, say, close to measure 0 that doesn't satisfy these concentration inequalities, is it likely to evolve? Is it likely to leave that subspace of measure 0 and evolve into the rest of the hypersphere, and then spend most of its time satisfying the conditions that we're interested in? So that's what von Neumann proves. And so in setting up the theorem or describing the theorem, let's use a full set of mutually commuting macroscopic operators called M sub I. This is, again, von Neumann's notation. And those are coarse-grained versions of things like the total energy of the system, the momentum P, which could be the momentum of the ball, Q, which is the macroscopic coarse-grained version of the position of the center of mass of the ball. And we restrict ourselves to a specific energy shell with some fixed macroscopic energy. That, of course, is a very degenerate space with lots of actually microscopic states of slightly different energy, but very close to that macroscopic energy. And then there were also many individual phase space cells with different macroscopic P and Q. And of course, you can add other quantities into this list of macroscopic operators if you want, but the simplest thing to consider is just that Brownian motion case where it's really just capital P and capital Q that you're focused on. Now, if you restrict attention to a specific energy cell with dimension capital D, you can further partition that into subspaces with definite values of each of the macroscopic variables Mi, and nu labels each of those sets of values. And let d nu denote the dimensionality of the subspace with values labeled by nu, so that the total dimensionality of the Hilbert space of the system, capital D, is just the sum over all the different nus of the dimensionality d sub nu. Okay, so von Neumann's theorem states that for any initial state psi 0, so there's no restriction on the initial state the system begins in, and almost any Hamiltonian H, in the long run, the system spends almost all of its time in a typical state, where typical is defined as having the following property. The expectation of the projection operator onto a particular nu state is approximately the ratio between d nu and capital D. Okay, so basically the likelihood or not the likelihood, but the coefficient of the expansion of the full state of the system to be in one of the phase space cells is proportional to just the dimensionality of the Hilbert space of that phase space cell relative to the total Hilbert space describing the entire system. And that is really the result that we want. It then implies that, say, for example, in the case of a box where there's say the bottom of the box is flat and there isn't a very strong potential, and so the ball can random walk to any corner of the box and there's no preferred position in the box for the ball, that all of the individual phase space configurations with the ball in different positions are roughly equally likely, and that you end up with a macroscopic superposition of those possibilities. Now, in proving the theorem, there are two technical conditions that are required. One is the absence of exact degeneracies. So that would be unlikely for a realistic box in the absence of exact symmetry. So that definition is almost certainly satisfied by realistic systems. And then there's a technical condition in the sort of heavy analysis that von Neumann has to do. There's a technical condition which relies on it that, it can be guaranteed by a relation between the specific energy eigenstate basis for the total system and the nu basis for the macroscopic states. And what you can show is that, this was shown by Ryman in 2015, in the limit of large number of degrees of freedom, the second technical condition is violated only for an exponentially vanishing set of macroscopic operators that one might define. And so therefore, by perturbing those macroscopic operators a little bit, which you don't care about because there's a very super redundant set of possible macroscopic operators, generally you'll be able to obtain the result for any realistic system. Okay, now in the discussion we've been referring constantly back to this example of Brownian motion. However, it's important to note that the conclusion can be generalized to almost any system which is complex, so it lives in a high-dimensional space. There are the technical conditions that I just mentioned, but they're likely to be satisfied. And then the other key thing is that the dynamics permit multiple macroscopic outcomes. So as long as the system is something that can evolve, it starts in some initial state psi 0, but it could evolve into different possibilities which are macroscopically different from each other, then von Neumann's theorem guarantees that if you leave the system alone and you come back after waiting long enough, you'll find it in a macroscopic superposition which is sampling all of those different possibilities. So that's a very strong statement, and it's very general. It applies to almost all systems that we're familiar with. There are some low number of spatial dimensions like d equals 1 or d equals 2, systems which condensed matter physicists are extremely interested in which thermalization does not occur. So even ordinary statistical thermalization does not occur, and the system is kind of trapped in a fixed set of in a fixed subspace of the larger Hilbert space. So those are counterexamples, but those are very unusual systems, and I believe there are some, I think, fairly plausible conjectures that it can't happen in more than, say, one or two spatial dimensions. So say in D equals 3 plus 1, which seems to be our universe, there don't seem to be good examples of these. They're called many-body localized systems that exhibit many-body localization. That's the only set of counterexamples that are known, but again, those are fairly unique systems. Now, let me now give a very simple kind of semi-classical discussion of why this result sort of had to be true. Okay, and it's just going to use these two ingredients. There are amplitudes for the ball to start at some x, be very well localized at that x, but end up, you open the box later and you observe it and you find it some macroscopically different position y. As long as that's the case, then it should be plausible to you that psi could evolve into this kind of macroscopic superposition, which is given at the bottom of the slide. Okay, so what's this quasi-classical explanation? So the ball is obviously subject to fluctuations arising from the collisions of the gas, and that is in fact what we know of as Brownian motion, right? Brownian motion is the result of those collisions and fluctuations. And so we have non-zero quantum amplitudes. So these are fully quantum amplitudes to go from x to y. It literally means that even if we start with the wave function of the ball highly localized at x, by some later time it has a projection onto a state which is highly localized at y. And we just accept that as a description of Brownian motion. But because Schrödinger dynamics is linear, if I leave the system by itself, then each of these quantum amplitudes has to occur in the superposition of possible evolutions of the ball. And so it should be plausible to you that psi actually evolves into a superposition state simply as a consequence of linearity. And really, that's all that statement says, that capital psi of t goes to infinity can later be written in this superposition of different psi nus. Psi nus represent the ball having random walk to a different location in the box. The only thing that is specific here is that we're very careful about how we can decompose this global wave function psi into orthogonal branches which differ macroscopically. They have to differ macroscopically because, as we said, the ball is solid and it excludes, the gas molecules cannot occupy the same space as the ball. And so when the ball is at coordinate x, that means that the distribution of the gas molecules, which are described by phi sub nu, not psi sub nu, but phi sub nu in this equation, that distribution reflects that exclusion property, and so the gas molecules can't occupy the region close to x. Similarly, when the ball is at y, they can't occupy the region close to y. So phi sub nus are macroscopically different from each other, and psi sub nus are macroscopically different from each other, and the whole thing is a superposition of macroscopically different quantum states. Now, what we gain from this quasi-classical or intuitive analysis is that it becomes plausible that the time scale, the t goes to infinity time scale required for this to happen, for this evolution to occur, is really only controlled by that of the original Brownian random walk. So if just under very elementary considerations, I conclude that it would take 10 to the 5th seconds for the ball to random walk from x to basically any other point in the box, that is the same time scale under which you would expect psi, the global wave function, to evolve into this macroscopic superposition state. In other words, because von Neumann had to take t to infinity to prove his theorem, it leaves the possibility that the result is only something that applies in truly the limit of time goes to infinity. But if you think about it in this simple intuitive way, it's clear that it should start to approach the sort of equilibrium or final global state, capital psi, already in a fixed time scale, which is roughly that or characterized by the Brownian random walk time scale. So it's not something mysterious in sort of super long time quantum dynamics. It's really just the familiar quantum random walk that you already know about. Okay, so to summarize that, perhaps it's unsurprising that after sufficient time, the wave function of the ball is roughly uniformly distributed over the box, and we can kind of guess how long that takes. However, what is surprising, or may be surprising, is that the global state is a macroscopic superposition state. And that is established rather explicitly through our analysis, that C nu, psi nu, phi nu is actually a set of, it is itself a superposition of macroscopically different states. And the long timescale characteristics of the global state psi can be established rigorously, almost independent of the specific dynamics. So, of course, the specific timescale that's required depends on the dynamics, but the fact that it achieves this state eventually can be proved rigorously, really without making any strong assumptions about the dynamics. Okay, so the result we proved is that macroscopic superposition states are ubiquitous. You take a complex system, you leave it alone, it's in a box perhaps, and you come back after waiting long enough, you open the box, you should find that it's in a macroscopic superposition state. And of course, this kind of macroscopic superposition state is familiar to anyone who's studied many worlds, or what's sometimes called no-collapse quantum mechanics, so quantum mechanics in which everything is described by just a Schrodinger equation that evolves unitarily and linearly at all times. And this view of quantum mechanics is typically introduced starting with the measurement process. So let me just do that to make a connection between the result we proved and quantum foundations. Okay, so let's think of the simplest possible measurement that you can do. Let's suppose I have a single qubit, and let M be a macroscopic device which measures the spin of the qubit along a particular axis. And the eigenstates of spin along that axis will be denoted plus or minus. And we define the operation of the measuring system, Stern-Gerlach device, for example, to be the following. If I start with the qubit in the plus state and it interacts with the measuring device, I end up in a final state S plus. S plus means it's the total system, but the apparatus has recorded in some macroscopic way or super redundant way, the apparatus M has recorded the plus outcome after interacting with the plus state. And similarly with the minus state. So minus spin qubit goes in to Stern-Gerlach machine, it's deflected down. A big green light goes off because the down deflected qubit is detected. And the photons from the big green light going off constitute a record of the outcome. And so that would be state S minus. So we just defined how a measuring device works. But once you've given the definition, you can just ask, well, what happens to a superposition state? Let's suppose I have psi qubit, and it's a superposition state of the plus and minus states. It could even be, for example, spin in the plus x direction instead of the plus or minus z direction, which enters the device M. And the device M here could secretly just be a Stern-Gerlach device. So in the conventional formulation, which actually is due to von Neumann, I mean, he's the one who sort of made this separation between unitary Schrodinger evolution and quantum projection after measurement. In the conventional formulation, you have measurement collapse, and one of the two final states, S plus or S minus, is realized, but not both. And then at this point, probability enters the theory. There's a probability of C plus squared or C minus squared of obtaining the S plus outcome or the S minus outcome. So this is the familiar type 1 evolution of the system according to the Schrodinger equation, but then when a, quote, magical measurement M occurs, then there's a projection, which is non-unitary, that happens. And of course, many people are uncomfortable with this because it's never really fully defined what causes a measurement, what kinds of quantum objects or classical objects are capable of producing this measurement projection. And when does the system just evolve according to Schrodinger's equation, and when does it not? When is it actually subject to this projection? Now, if you make the assumption that the combined system of, say, qubit and Stern-Gerlach machine evolves according to the Schrodinger equation, so that would imply linearly, then you get something very different. So when you send in the superposition state into the experiment, and again, this superposition state could just be qubit spin plus x instead of plus c or minus c. The linearity implies that you end up in the final state with a superposition of the state of the actual measuring device. And this seems counter to actual experience, right? So it seems like when we make measurements, we always get a single outcome. We never get a superposition state. My Stern-Gerlach machine doesn't end up in a superposition state. So it's sort of this feeling that makes us think that macroscopic superposition states are fragile because we don't see them very often. We have to labor very hard to make them in a quantum optics lab or a quantum computing experiment. And if we don't do the experiment quite right, the macroscopic superposition falls apart. But the key observation, which really goes under the name of decoherence theory, is that if you're an observer in the state S+, you might not be aware of the existence of the second branch of the wave function, which is in state S-, for dynamical reasons. And these dynamical reasons, which cause the evolution of S+ to be largely independent of S-, which is another way of saying that they just basically don't interact, or the interactions between them are negligible, that phenomenon is called decoherence. So any object that's sufficiently complex to be considered a measuring device or an observer using a measuring device, usually typically that kind of object is regarded as semi-classical, any object of that type will have to have many degrees of freedom. And a measurement would only be said to have occurred if the states m measured plus and m measured minus are very different. So in other words, the red light bulb went off, or the green light bulb went off, or my brain recorded seeing the red light go off, or my brain recorded the green light going off. Those are two very different quantum states, descriptions or quantum states, outcome states of the same system. And if you do end up with those two very different macroscopic states of, say, the light bulb or my brain observing the light bulb, that implies that the overlap of the two vectors in the big Hilbert space, two vectors m plus and m minus, is exponentially small in the macroscopic number of degrees of freedom. So what that means, if you analyze the dynamics carefully, is the future evolution of m plus and m minus are very unlikely to affect each other strongly because the overlap of the two vectors is so small. So this is actually a dynamical observation, which is made about macroscopic systems, and it, in some sense, resolves this problem of wave function collapse. The way that John Bell put it, for all practical purposes, an observer, which is described by m+, could be completely unaware of the existence of m-. And the way the language is defined, they are said to have decohered from each other. So m+ and m- have decohered from each other. And this corresponds to the phenomenology that we experience in quantum mechanics in doing everyday physics experiments. Each of the two observers will perceive a collapse to have happened. It will seem to them that the projection, von Neumann projection, happened, although the evolution of the overall system, including themselves, might have been completely linear and continued according to the Schrodinger equation. So wave function projection is not a real thing. It is an apparent phenomenon, and it is a result of decoherence. So the result that we proved, based on the quantum ergodic theorem, shows that macroscopic superpositions of outcome states like S+ and S- that we defined here for the Stern-Gerlach machine are ubiquitous under Schrodinger evolution. They're not surprising. In fact, it's very hard to construct a system that doesn't evolve into a superposition of outcome states like S+ and S-. So interactions such as the scattering of particles in Brownian motion will lead to such states with the solid ball in different places in the box, even if observers in the closed system are unaware of it. So in other words, if I add observers to the box, so in addition to the gas atoms floating around, I have a fly or I have an amoeba or a person floating around in the box, the theorem applies to them as well. So as long as the Schrodinger equation is describing what is happening inside the box, we will end up with a total wave function in which the, quote, observers or the environment of the ball, the solid ball, also end up in a macroscopic superposition state. So to summarize, macroscopic superpositions are not fragile. They're rather ubiquitous. What is fragile is the capability of a macroscopic observer to detect the existence of other branches of the superposition. And that phenomenon is well understood now as decoherence. So on this last slide, I just want to emphasize again, so this is our model system again, solid ball surrounded by gas molecules. But I could certainly add to the environment of gas molecules an amoeba. I could add a cat. I could add a robot. I could add a scientist. And as long as those things that I add to the system, the atoms which make up the amoeba or make up the robot or make up the scientist, as long as those atoms individually are governed by the Schrodinger equation, the result that we proved actually continues to hold. That the global state describing the entire system, including the robot, will evolve into a macroscopic superposition state. And so that's the conclusion of my talk. Thanks for listening.